So, in the previous lecture we finished the ideas behind time frequency representation. So, in this lecture we will talk about Fourier series, various notions of convergence, properties and so on. So, we will go slightly into some details concerning the Fourier series. Right. Okay. Now, just to recall, most of you would have done this over the interval minus pi to pi. You can expand f of x as a naught plus summation k equals 1 to infinity a k cos k x plus b k sin k x. Okay, so, this is a general representation for a series. A naught is your DC term, which is 1 upon 2 pi integral minus pi to pi f of x dx, and these a k's are basically the Fourier coefficients. A n is given by 1 upon pi integral minus pi to plus pi f of x cos n x dx, and b n is basically the inner product of f of x with sin n x, right, and a i's and b i's are the Fourier coefficients. Now, let us delve a little carefully. Consider the function f of x equals x on minus pi to pi. So, this function is clearly an odd function, right. It is straightforward, it is an odd function. Therefore, you do not have these ai's and you can compute these bi's. So, let us say the bk coefficient is given by this formula, and if you did carefully integration by parts and computed bk, you can say that f of x is summation k equals 1 to infinity 2 times minus 1 power k plus 1 upon k sin k x, right. This is what you get as an expansion, right, which most of you would have done in your undergraduate in electrical sciences, whichever, electronics, communication, electrical, whichever stream in electrical sciences, you would have done this. Now, for this example, f of x is not 2 pi periodic. So, let us form a function f tilde which is a periodic extension of f. Okay. So, if you just sketch this function, right, you get these, get the function. So, 0 then extend it by 2 pi either side, you can just write this as, right. Now, observe that there are these jump points like plus minus k pi are points of discontinuities or jump form of discontinuity. So, f of x converges to f tilde x at points where f tilde is continuous. However, we have discontinuity points at plus minus k pi where k is some integer. Right, and at those points, at these, we will have to prove this result anyway, we will go into the details and depth through the subsequent lectures. At these points, f of x will converge to f of k pi plus f of k pi minus, that means you take the left hand limit, right hand limit and you take the mean value. Of course, when we observe this figure, the discontinuity points are at odd multiples of k here. So, therefore, I would just say that this is going to be at plus minus 2k plus 1 times pi and k belongs to a set of integers, positive integers, and you have to include 0 as well. And we would have basically studied this in our undergraduate curriculum. Okay. So, now let us look at the finite sum case. So, n instead of being infinite, capital N being infinite is now finite. That means, I take the first capital N terms in the Fourier series expansion, and then I compute. Now, there is a weird thing that one would notice. As a function of x, if you plot the function, right, ideally it has to be like this. Now, at this point there is a sharp jump, right. So, if you plot this and graph this function S n of x, S capital N of x for different values of n, you will see that there will be some blips at this point, and then the signal just jumps through this point. I mean, from at this point pi, there is some positive value it has, and from some positive value it has to suddenly jump to a negative value. The swing is really sharp, right. That means the graph of this function must travel from if you just look at what this value is, right. I mean, f of x equals x. So, therefore, this point is pi, this point is minus pi on the ordinates, right. So, from pi to minus pi it has to just jump in a very small interval, and this you can sort of imagine like a waterfall, or it is called the waterfall effect. So, imagine you have a river, it is going straight, and then as you approach a waterfall, I do not think anybody would want to just go through the process of going through the boat on the river with leading to a waterfall, because you can see the rapids, right. As the rapids increase, and exactly the same fluctuation phenomenon which is happening here, there is rapids and then there is a huge fall, right. So, we would like to investigate to, so this is because of a truncation and this point of discontinuity. So, at this point of discontinuity you are trying to represent this summation, and this is not accurate, limit is not defined at this point, there is a sharp jump, right. So, therefore, at this point of discontinuity the accuracy of these blips it really gets worse, right. I mean, as that means if you sketch 20, 100, 1000 so on for n, you can see that there is a variation in this height and then the oscillations, and this phenomenon is called Gibbs effect. So, I call these as blips. Accuracy of the blips around the discontinuity points gets worse. So, what it means, the graph of Sn of x for small finite n, capital N, say n equals, I just take 10 terms, right, must travel from pi to minus pi in a very short interval. So, this is something like the like imagine you have a very small orifice and you just have to just go through that point of discontinuity, right. So, the blips occurring just before and after the points of discontinuity is called Gibbs effect. This is a very, very important phenomenon. I don't know, I mean you have to really exercise this, you have to write a program, compute this and then observe what is happening, right. And an artist's way of visualization of the Gibbs phenomenon is imagining that you are going through a river rapid and then there is, and if you are finding the oscillations are becoming larger, you better beware that there is a steep fall expected, right. It's like that. Now, a few things to note. The height of the blip is approximately the same for large n, and the width gets smaller as n gets larger. So, this is through observations. Actually, I will give you a homework when you will actually prove that these results are indeed correct. So, what I would like to do is, like you to do is, plot Sn of x for n equals 10, say 100, 1000 dot dot, and sketch this, observe Gibbs effect. Then I would also want you to investigate for a sawtooth wave which is given by S of t equals t 0 less than or equal to t less than or equal to pi upon 2 and pi minus t from pi upon 2 less than or equal to t less than or equal to pi, right. I give you this function, observe what do you observe and what can you conclude from this. So, this is just a homework exercise for you. So, it is just not computing the Fourier series as what we have done. I mean, we have to understand many subtle details in this series expansion, right. Can we approximate all functions? Are there any conditions? What does the function take at the point of continuity? What does it take at the point of discontinuity, right, so on and so forth, and these subtle issues are what we will be dealing with through the next set of lectures. Okay. So, we will first start with a theorem. Suppose f is a piecewise continuous function on the interval a less than or equal to x less than or equal to b, then limit k going to infinity integral a to b f of x cos kx dx is limit k going to infinity integral a to b f of x sin kx dx, and this is equal to 0. F is a piecewise continuous function. So, what does this mean? So, a piecewise continuous function has only finite number of discontinuities, right, at those piecewise points, and therefore, there are only a finite number of Fourier coefficients larger than a certain absolute value given a certain positive number, right. I give you certain positive number, there are only a finite number of Fourier coefficients which are bigger than this number, and basically this implies you can do data compression for these type of functions or signals. I use them interchangeably, right. So, let us see the proof of this result. So, you can imagine that you have a high frequency wave this is almost like my sine wave, right, and I have some function that I am sketching. This is y equals f of x, and this is like my y equals sin kx. Okay. Now, as the frequency increases, right, f of x is nearly constant between two adjacent periods of sin kx and cos kx, right. So, what is happening is if I take imagine this is really very high frequency and I have a function here, some function, I increase this frequency a lot, right. You can say that this between these two peaks it is nearly constant, right. I mean, this is really not a very high frequency, but imagine terahertz, if tera is not sufficient for you, just bring in some huge number for frequency, that means it is almost you really cannot see it, it is as if it is piecewise flat. I mean, this is even high frequency, probably, right. If you just put a function around that, you probably see it's constant, right. Now, this is the idea. Now, we take that high frequency and then we you take the inner product of that with this function and let the frequency go to infinity, we have to show that this result is 0. I mean you can imagine why this is true, because over a cycle the value is constant and the swing basically gives you a positive value and a negative value. It should hopefully sort of cancel out, right. But we will actually prove this result. Now as the frequency k increases, f of x is nearly constant on two adjacent periods of sin kx and cos kx. The integral over each such small period is 0 over piecewise intervals. Now in the case of a differentiable function f, let us assume that this function is differentiable. Now integral a to b f of x cos kx dx, I am considering this integral, this inner product here. So this is sin kx, I am integrating this by parts, first function, integral of the second function minus integral of the second function, derivative of the first function. Since I need to take the derivative of the first function, I am introducing that it is a differentiable function. Okay. So this also gives you a hint sort of how mathematicians work, is also playing around with these quantities, right. I am integrating the second function from a to b minus integral from a to b of this form. Now let us look at each of these terms. I will call it 1, I call it 2. So now term 1 is basically sin kb f of b minus sin ka f of a divided by k. Now f of x is nearly constant and therefore the sign is bounded function. So therefore this basically heads to 0, this heads to 0, and in the second part, right. So you have to use the fact that when k goes large, f of b is f of a, right, and then apply this rule here. It's straightforward. And then in this part the derivative of this function is going to be 0 because it is a constant function, so this vanishes. So 2 is also heads to 0 because f of x is constant when this is really large because of this observation. Okay. So with this we are ready to discuss the notion of convergence at a point of continuity. Okay, so this is so just going back, this concludes. I mean, you can take the sine, you can take the cos, it's the same thing, it doesn't really matter. So therefore, this concludes the proof. So let us stop here. If you have any questions, we will take it and then we will get on to the next.